We use NumPy for numerical computing, and the numbers that we do our computations with we store in Numpy Arrays. So how do we create Numpy Arrays? The simplest example, so the creation from lists, we already saw in the previous video. And here we just call np.array with a list. This would also work with a tuple. Creating an array from a list is useful when we have specific values in mind, like 10 to 35. If we want to create arrays with numbers that follow some structure, we can use Numpy Functions. And these are also faster than Python's built-in functions. So what do I mean by numbers with structure? For example, Python provides the range function. And with this range function, we can create lists. And these numbers here are not some specific values, but they're structured in range 0 to 5. And so NumPy provides us with np.arange. And np.arange works the same as range, so we can give the function a start parameter, a stop parameter, and a step size. And this then creates an array starting at 2, up to, but not including 14, and we have a step size of 2 between the values. And this NumPy function is significantly faster than Python's built-in range function. So here we are creating first with the range 1 million values, and then from the range object we create the NumPy array, and that takes 46 milliseconds. And if we instead directly use the np.arange, again with 1 million values, it takes way less time. And it's actually 70 times faster. A very similar function to arange is Linspace. To this function we also give a start and a stop argument, but then instead of step size, we give it a num argument. And this will also determine the step size, but only indirectly, because it determines the amount of numbers from this interval. And another difference is that the stop is included. So we start at -5, and then the values are increasing, always with the same difference between them, up until we arrive at 5. We can also initialize our arrays with constant values. For example, we have the np.zeros, and this will create an array with only zeros. So we write np.zeros and give it 3 as an argument, and that gives us an array with 3 values that are all 0. We can also give a shape argument to the np.zeros, and that allows us to create multidimensional arrays. Later you will hear more about this shape. For now, so that you can understand this code here, imagine that in the deepest brackets we have 3 values, and in the second deepest brackets we have 4 elements, so 1, 2, 3, 4, and then in the highest brackets we have 2 elements, 1, 2. Very similar to np.zeros are np.ones, np.empty, and np.full. Here we can also initialize the arrays with either a single value or a shape argument. And as we expect, np.ones gives us an array with only ones. np.empty also looks like it would give us an array with only ones, but what's actually happening is that it fills the array with whatever is left in memory. And that makes it faster than np.ones or np.zeros. And here you can see how much faster, so 38 times. And so we can use np.empty when we don't care about what kind of values our array contains, but we just care about the shape. Kind of opposed to that is the np.full. Here we care about the values, or rather we care about one value. So the np.full allows us to fill an array with the same value. And again, it takes a shape argument, and we can specify with what value we want to fill our array. So here is filled with 42. Now for you, a small exercise. Your task is to create a 3x3 array that only consists of the boolean true. Okay, now onto the anatomy of arrays. So what kind of attributes our arrays have. One important attribute is the dtype, which tells us the data type of an array. And so our arrays can contain booleans, ints, unsigned ints, so ints with only positive values, floats, complex numbers, and these can all come in different byte sizes. Maybe you're familiar with the binary system. So if we have 1 bit, we can represent the number 0 and 1. If we have 2 bits, we can also represent 2 or 3. And the more bits we have, the higher our numbers can be. And also for floats, the more accurate our numbers get. So sometimes a 8-bit int is enough, and sometimes we want 64-bit. And that really depends on what we're doing. And usually we don't have to really care about these data types, but sometimes it can lead to problems, which we will cover later. Okay, we can also store strings and other Python objects, but that has very few use cases since after all we're doing numerical computing. Okay, so here we are creating an array with the values 1, 2, 3, 4, and these are all integers. So we can pass as a parameter for dtype the string integer or int. And if we check the dtype, we see it's of type int64. And so that means our integers are represented with 64 bits. If the dtype that we specify does not match the values, so here we're using the same values from above, but we specify the dtype as boolean, and so NumPy will cast everything to that data type. So instead of 0, we get false, instead of 1, we get true, and then so on. If we don't specify any data type, NumPy will choose the smallest common denominator. So that will be the data type that we can describe most values with. In our case, our values here contain integers but also floats. And so NumPy will choose for the data type the float 64, since we can represent integers as floats, but not floats as integers. What's really important is that once the data type is set, everything that's added or changed in that array will be transformed to that data type. So here we have our NumPy array and we specify for the dtype integer, and then when we try changing the first value to 1.5, it will convert that into the integer 1. Now onto the problems or challenges that come with NumPy's data types. For example, we have the data type uint8, and with 8 bits we can specify numbers which are positive up to 255. After that our number kind of overflows. And so here our array has a 1 as its second value, and if we add to that value 255, we would reach 256, which is too high, and so it again starts at 0. Another problem comes up when we compare NumPy types to standard Python types. So what happens here is that we compute 1.2 minus 1, that is stored in value, and then from this value we create a NumPy array with the data type float32. And if we now compare the value to the array containing that value, we see that they are not equal. And that is because their types are different. So the value is using a standard Python type, which is just float, and the NumPy array is using numpy.float32. And while both are floats, the difference is that Python uses by default 64 bits. And because 64 is more than 32, the float calculation will be more accurate. So we can see this value here is closer to 0.2 than this value here. And so to fix this issue, we could either change the NumPy data type also to 64. Now they're equal, or we could use the NumPy function isClose. So we call np.isClose and pass the value and then the array with the value. And that tells us that they are close. Really close, of course. If you're interested what's up with these floats and why 1.2 minus 1 is not 0.2 but these weird values here, you can check out this link. Next up we have the shape and endim attribute. Shape tells us the shape of an array, and what that describes is the number of elements that we have in each dimension. Endim will tell us the number of dimensions in total. So let's start with one dimension. So here we just have a normal list with the values 1, 2, 3, 4, and we create an array from that, and the shape of that array will be 4, because in the first and only dimension we have 4 elements. And so of course, because we only have one dimension, endim also returns 1. Next up, 2 dimensions. Now looking at this code here, you might say, aren't these 3 dimensions? And one thing that might help you understand is imagining that if we are at a certain point in this array, we could either iterate in this dimension, so to the right, or downwards in the second dimension. And if you're coming from other fields, you might be thinking about degrees of freedom, so that these are 12 values that we could change, or a 12-dimensional space that we could move through. But that's of course not the case here, and so maybe it's best to imagine that we can write in this dimension, and for example add a value to here, and then we can also write in the second dimension, so adding different values here. And thinking about it, it really looks two-dimensional. So maybe let's not overcomplicate things and check out the shape here. This will tell us 3, 4. And now because we added some values, you have to run it again. And now it's telling us 3, 5. And that means in the first dimension, we have 3 values. So 1, 2, 3. And then going deeper into the second dimension, we have 5 values each. And in total, we have 2 dimensions. Of course, we can also access the elements in these higher dimensional arrays. And so for each dimension, we specify a separate index. And so here we take from the first dimension the second element, and then in the second dimension from the same element, also the second element. So the 1 takes us in the first dimension to this array here, and then from this element in the second dimension, we take the second element, so the 2 here. And so we get 2 as an output. Of course, we can also override values that way, so here we assign to the same spot a 10, and now we have a 10 in our array. Okay, finally 3 dimensions. To make our code more concise, we're using a different syntax here. And this might also help us in understanding dimensions. So we have our first dimension, in there we have 4 elements, then we multiply that, giving us a second dimension with 3 elements, and then we multiply that again, giving us a third dimension, now with 6 elements. And so you can see the 6 elements here, 1, 2, 3, 4, 5, 6, each of them containing 3 elements, 1, 2, 3, and so on, and then each of them contain the 1, 2, 3, 4. And so the shape is 6, 3, 4, going from the outer to the inner brackets, and in total we have 3 dimensions. As for other attributes, what's really useful is the transpose, which can appear in various data science contexts. And of course, there's also so much more, which we'll of course not go into, but there's a good chance that if you Google, can my array do that or does it have this attribute, then you'll find an answer that takes you to one of these things here.